Hey everybody! Welcome to our intro video for the Extra Credit Lab. It's on Cepheids and Hubble's Law. And this is a really pretty straightforward kind of fun thing where you will start off measuring the period of a Cepheid variable star and wind up computing the age of the universe. That's pretty far out when you think about it. Before I get to all that, let me tell you what's going to happen here. This one will be available to you on Sunday, July 26th in the morning, and you'll be handing it in before Monday, August 3rd at 7 p.m. That's shifted 24 hours ahead because the semester ends August 4th and I have to be doing other things and correcting labs on that day. So that's all there is to this. Now let's take a look at this. Here you're actually seeing the data that you're going to actually use. This is the Cepheid variable star in the galaxy M100. Now that's a galaxy that's about the same size as the Milky Way and probably has 300 or 400 billion stars in it. So this is a magnificent structure. And we see that there are Cepheids in the center of all the frames of all 6 images. Notice the dates for each image are given right here. Now you can do this by using Seeds, which has maybe a better image on page 283. You'll see the same thing. And it works better in the text if you have like a magnifier, and I think it works better using these images if you don't. But let's go ahead and just talk about that. In the lab itself, or at least the instructions in the Canvas instructions, I give several comments about how to actually go about doing this lab, in addition to the ones mentioned here. So let me do that here with you right now. Notice the Cepheids change brightness. See, this thing has gotten a lot dimmer than it was over here, and likewise here. What you need to do is actually find one complete cycle of these things, and what it suggests you should do is start here and just carefully eyeball all of these. If you were an astronomer in an observatory, you'd simply scan the images, and that would tell you what the period was by how the images respond over time. But you're going to do that by your eyeball. Obviously, we're dim here, and we're bright here and here. And you need to try to figure out what the actual period is. Now, this isn't the case, but let's imagine for a second that from April 23rd to May 4th was one period. That's not the case. But you have to remember you're going to have to subtract April 23rd from May 4th, so you're going to use a calendar to find out exactly how many days there were between those two dates. Now, so the first thing you do is you estimate the period based on your eyeballing of these pictures, and you write that down there. Then on then point number 2, you use the period luminosity relation. That's on page 255 in Seeds as well. In fact, without this, you can't do this labs, but it's very simple. You have to realize that the Cepheids we're looking at in M100 are type 1, and so you use the top curve in figure 12.4. That's real easy. It's just a plot of absolute magnitude on the y-axis versus period on the x-axis. So whatever your period turns out to be, if it's 5 days, you go over to 5, then you go up to the type 1 Cepheid curve, and then you go over to the y-axis and actually read off the absolute magnitude. And that's all there is for this. And then you write it down here. Now, it doesn't tell you in the lab, but the absolute magnitude is simply the brightness, the apparent brightness a star would have if it were 10 parsecs from us. That's a standard distance. A parsec is 3.26 light years. Okay, so that's something, if you want to convert between the two, that'll help. Now, number 3, Hubble Space Telescope allows us to convert this absolute magnitude. Remember, absolute magnitude actually is related to luminosity, but we won't touch that part of it here. The number plus 25.9 is the apparent magnitude of this Cepheid, and so that goes in here, and your absolute magnitude that you just computed in point 2 goes in here, keeping in mind the signs, SIGNs, for these things. And remember that the parentheses here, we calculate a number within them first, then we divide the whole thing by 5. This is an exponent now. It's 10 to that exponent. So in your calculator, you have to ask the calculator what 10 to this exponent is, what the value of that is. If you don't have a calculator that can do that, you can do it on the internet. Just go into Google and say 10 to the what power is what. It'll actually tell you. Now, when you get this distance, it's going to be in parsecs. That's important to know, because they want you to convert that into megaparsecs. That's easy. You just divide the number you get, d, by a million, because a mega is a million. So if this is x number of parsecs, we divide that by a million. That'll give us what the distance is in megaparsecs. If you divide that by 3.26, it'll give it to you in million light years. I'm not really hot about using light years here, but that might be interesting for one thing to do there. Now, number 4. With the spectroscope, the Hubble Space Telescope finds that the hydrogen alpha line, this is a spectral line of hydrogen, which is normally seen at 65, 63 angstroms. Angstrom is just a unit of wavelength. You don't have to know specifically what that is. But the hydrogen alpha line is shifted, redshifted to 65, 90 angstroms. So the delta lambda here is simply the difference between 65, 90 and 65, 63. And you write that number right there. And the lambda to 0 is simply 65, 63. So you take that ratio there and put it down here. Notice it's multiplied by c, the speed of light. Then over here they have you do that multiplication, and this will actually be your velocity of recession of the Cepheid and the galaxy which is carrying the Cepheid along, more importantly. Now we're going to calculate h. Normally we would do this with several galaxies and get several different points, but we're going to do this with just one to make it quicker, and it'll still illustrate how this is done. Hubble's law says the velocity of recession of the galaxy is equal to Hubble's constant, which we're going to calculate, times the distance of the galaxy. We have now found the velocity and the distance, so we simply divide v by d, and that gives us our h. And we have to notice the h is in kilometers per second per megaparsecs. This means that for every megaparsec you go out into space, it increases by this number of kilometers per second. Do not do the kilometers per second per million light years. That's of no interest really. But this is the one that matters, the big enchilada. Number 6 says your h should be something like 70 kilometers per second per megaparsec. It won't be exactly that, so don't worry if it's not. And they have you calculate the percent error. Just follow those instructions. Number 7, we're not going to do it like this. I do want you to compute the Hubble time, but in the Canvas instructions for this, you'll see there's a very simple way to do this without going through this chamber of horrors right here. Oof, boy, it gives me a migraine just looking at it. All you have to do is take the h you've got, divide it into 1. So you've got 1 divided by h, and all you have to do is multiply that by 1 trillion, and that'll give you the Hubble time in years. A trillion is 1 followed by 12 zeros, or 10 to the 12th power. And that, friends, is all there is to that. If you have any questions, I hope you have fun with this. Alert me on Canvas if you do.